Hi, everyone. This is the lecture for Module 7, which gives an introduction to the concept of Docker. So, pop quiz. What is virtual hardware? Thinking about this idea, you might not have much exposure to virtual hardware, but take a moment to think about, what it means to be virtual. Um, Essentially, you have physical hardware, but what does it mean to be virtual hardware? And so this lecture will talk about some of this concept of virtualization and then get into Docker concepts. So first, a condensed history about virtualization. So think back to the 1960s. Some of the first computers were created and they literally operated off of cards that had holes punched in them. And a computer program was that card. And, a person would load a machine with cards or a program and then run it. And that's an example of a single user computer. And it's all it did. It only knew the idea of one person operating it. Well, fast forward to the 60s and into the 70s, you get this idea of multiple user computers. So you had the idea that you had a computer that had multiple user accounts on it. And so this one user had programs and files that were installed just for that user. And then you had another user to log into this computer and they would have a home drive and files that belonged to them. So that's kind of the first concept of a virtual user space. A person would log in with a username and password and they had their own virtual folder that held their data. That's kind of the first introduction into virtualization. And then this idea grew into where you had concepts like mainframes, where you had a coaxial cable connected to a large computer that's down the hall, and this coaxial computer links your keyboard and your monitor to that computer, and I could be sitting in my office and typing and logging in with my user account and using data files and programs on the mainframe. And then the idea of physical servers where you install them into racks came into play, and these servers did specialized functions. And then fast forward a little bit further, these servers would become so powerful and so large where you might have one processor and 2 gigs of RAM. Well, the technology leaped forward, and you would have ideas where you would have servers with thousands of processors on them and gigabytes and gigabytes of RAM. And so it became inefficient to install one program on a server or 10 programs on a server. And what you would do is that you had this concept of virtualization became born. You could cordon off or pull out of 1,000 processors, you could pull out 4 processors and 2 gigs of RAM and give them to one virtual server. And that big server could run hundreds of little virtual servers all doing independent functions on there. So that's a big leap in history there, literally going back from the 60s to the 2000s. So the idea with servers is that they become, as the hardware becomes more powerful, new software is created to use the hardware more effectively. And so by the late 2000s, virtualization as a concept was the new drive in computing. It's really kind of when cloud computing was born, or the concept of cloud computer. You had thousands of virtual computers that were supporting multiple services, and that kind of created a cloud of services essentially. So one server becomes many of thousands of servers in that concept. So fast forward to 2014, Docker is born, and it's created to solve a new kind of problem. So what is the problem space? What's Docker trying to solve? Docker is a technology trying to solve the problem of how to package applications and services. So virtual machines, isolate system resources and provide a working environment. Docker's approach is to isolate individual applications. It's very specific to just isolate the individual applications and not an entire operating system. So Dockers boot up faster. They're really small. They could be, a Docker virtual system could be as small as 20 megabytes, and it spins up and runs something and shuts down. So it saves disk space, it saves system resources, because before there was this idea of Docker and containers, there were virtual machines that were larger in size. They could be anywhere from 300 megs to 40 gigs, and trying to manage thousands upon thousands of these servers. If you think about Google or Amazon or any large company, managing these servers, these virtual servers efficiently, effectively, it's just challenging. There's a lot of solutions to kind of manage these things, but Docker just does this idea a little bit better, and it focuses on just the application part. So both technologies are viable solutions to provide applications and services to customers. It's just the virtual machine footprint is bigger, and Docker's footprint is smaller and it runs faster. But the question is, when do you employ each technology? So with this graphic, I'm trying to explain or trying to compare, a virtual machine arrangement versus a Docker arrangement. So at these first three layers, the infrastructure, the host operating system, but then you have a change at the third layer where you have a hypervisor in virtual machine land, and a Docker, you have a Docker daemon, which also acts as a hypervisor essentially. But if you notice, the stack is a little bit smaller for Docker. They've eliminated this idea of having a guest operating system run application 1, application 2, and application 3. They put a Docker pushes that work into the Docker daemon, and all each individual Docker container does is run app 1, 2, or 3. Yeah. So let's try to think about the what, why, and when of Docker. So what is Docker? Docker is a tool designed to make it easier to create, deploy, and run applications. It derives its name from the shipping industry. That's why the logo is a whale with multiple little squares on it, because each square represents a container that's on like a large shipping container. It derives its name from the shipping industry, and it's developed by Docker Incorporated literally in March 2013. And it's a tool that is great at application distribution. It's great at deploying software. So why do we use Docker? It benefits both the developer and a system administrator, and ultimately the customer. Developers use Docker containers to develop software in an environment that works the same as the customer's environment. So it solves this, hey, the software worked on my machine. I don't understand why it doesn't work on yours. It's kind of a classic line from a developer. System administrators use containers to operate multiple containers on systems to increase computing density, scale resources during times of increased demand, and reduce management of application dependencies. And so what I mean by that is that, say that you deploy software that is dependent on having Apache, it's dependent on having SQL, it's dependent on having a Java environment. And so you might give this software to someone outside of a Docker, and when it goes to run, the software doesn't run because they don't have SQL installed, but they have Apache and Java. So what you're doing is you're creating a container of software that contains all of the dependencies that that application needs to run. So it's a way of deploying software in a container. Corporations use containers to more quickly deliver new features and software to their customers. So when should you use Docker? Well, we'll use it when you want to collaborate on an app's operating system with a team. Use Docker as version control for an entire app's operating system, or you want to use it when you need to run code on a laptop in the same environment as on the server, or vice versa. How do we use Docker? So there's certain concepts in Docker that we need to talk about. So we'll talk about the idea of images. So images are an image is every file that makes up just enough of the operating system to do what you need to do. It's a template that can be turned into what's called a container. You can also, the file is essentially a persistent script on how to build the operating system install components. So it's created with what is called a build file or a Docker file. And take note that I use a capital D there. If a Docker file has a lowercase d, it will not function correctly. It has to be a capital D. So the file itself is an inert, immutable file that is a snapshot of a container. And we'll talk more on that later. It's stored in a Docker registry like registry.hub.docker.com or in a private registry. Say that a company has some trade secrets in how they build their systems to run their software. They don't want people to know that. Well, you can have a local private registry in a corporation or a university. Or you can just use the publicly available registry at docker.com. So each Docker file has its own unique ID, and you as a software concept, think of images as a class in software. So as an example, how to run this software, how to create an image, as you would Docker run -ti, use the Debian operating system, use the stretch slim version of Debian, and then you'll use bash command line interface on that Docker. So that would run a Docker using Debian. So then we move to the next concept of containers and logging. So for containers, you can think of containers as an instance of a class. So if an image is like a class in software, the container itself is an instance of that class running, or container is a lightweight and portable encapsulations of an environment in which to run applications. And so this also has its own unique ID. An example of this, how to run a container is you type in Docker run -rm, meaning once you are completed running, delete yourself. And so again, we're doing -ti, and the I part of that is to give the person an interface so they can see what's going on. So we're running Debian stretch slim, giving a bash command, and then we're doing a -c to run the command, sleep for 5 seconds, and then type or print to the screen the command all done. And so that would take an image and run that as a container. The other idea or concept in Docker is logs. So Docker keeps the output of containers as long as that container is not deleted. So be mindful of your command output, as it can bog down the container. So kind of a Harry Potter reference is that it's like a Gemino curse or a double charm. Essentially, if you're running a Docker that is spewing output to a log file, it just keeps growing and growing and growing and growing. And so that's kind of what, it makes me think of the Harry Potter reference in that instance. So in order to see the log output from what happened on a container, you would type in docker-logs, Docker space log space my container ID. And so like I said, each container has its own unique ID, and they have their own log if you enable it. So then the next concept in Docker is the idea of volumes. So volumes are the preferred mechanism for persisting data generated by and used by Dockers. So the idea is that Dockers, can boot up quickly, and they can stop quickly and, delete and be gone. And so you don't want to do you don't want to do data storage necessarily on a Docker, but you do want to, if a Docker is performing a function and is modifying data, well, you want to use the idea of volumes. So Dockers can spin up, they can mount a volume and interact with data on that volume, and then the Docker can go away. So volumes can be shared among multiple containers. Volumes can be stored on remote hosts. And so there's two varieties. So there's this idea of persistent, and there's this idea of ephemeral. So with persistent, if a container goes away, the data persists on the volume. And with ephemeral, if a container goes away, the data evaporates. Like any data that you created, there's no hope of keeping it. It just uses RAM as its disk, and it evaporates. So it's not part of images, but rather volumes are initialized when a container is created. So you have to, if you're going to do a volume mount, you have to do it when you create the container. And so you can specify a volume in the Docker file as a path for the app to use in a container. So an example of all this is that, say you're going to do, okay, we're going to do Docker run, and then the file path that we're going to mount is this home Docker example, and it's going to mount to the shared -folder file or folder directory on your computer. And then you're going to run Debian Bash, the operating system Debian with the Bash terminal. So it's going to boot a Docker up, it's going to mount that path, and then it's going to run it using Debian and give you a Bash prompt so you can interact with that volume. Another concept of Docker is the idea of networking. So why create a computer if it doesn't talk to other people, right? So Docker creates 3 types of networks as it installs. It has a bridge, a node network option, and a host network. So Docker connects to the bridge network by default. It's trying to bridge through the network of a server to talk to the world. So Docker uses bridge networking to create virtual networks on the host system. Think of these as virtual software switches, basically a networking concept. You can create multiple private networks for containers to split them up as needed. You can cordon off that traffic so one container doesn't see traffic from another. It's basically in the Ethernet layer, and it moves data locally among containers. Then you have another IP layer that moves between networks, and then you have routing handled by Docker for traffic sent between bridges and out to the world. So an example of creating your networks as you run Docker is, you can type in Docker space network space create space a network called my-net, or Docker create dash name my Debian, and dash network my-net, and then dash publish to port 80 on the server, and then use Debian stretch. So what this is doing is it's creating a Docker container called my-Debian, and it's setting up a network called my-network, and the local port is 8080, but it's actually using port 80 so that it can host web pages and running Debian. And then so say that you go to a system that already has a network set up, you can use Docker network connect my-net to my-Debian. So the idea here is that my-net is the network that's already set up, and you just created a new Docker running Debian, and you want to connect that network to that Docker. That's the command you would run. So we talked about a little bit quickly about Docker registries. So Docker registries Docker images, are retrieved from registries, and registries manage and distribute images. Docker runs a registry for everyone, but also allows local institutions to run their own local private registries. An example of interfacing, from the command line is the type of command called Docker search Debian. So that goes out to the Docker registry and searches for all Docker images that use Debian. Important concept and idea here is that if you create an image, you do not want to put your password in this image, so you don't want to push images to the registry that contain passwords. Else anyone else can search in this public registry and know what your password is. So another idea is that it's a public registry, so keep in mind you don't necessarily know who has put or created a image that's in the registry. So be aware that as you download images, if you didn't build it yourself, be cautious. You want to trust places like Red Hat or CentOS or Debian, the companies themselves, for maintaining their own images. Those are more trusted. And in the registry, it tells you who builds these. And then so there's also this concept in registries where you're upvoting or starring or trusting different builds. And so with that concept in mind, just be cautious. It's just rule of the road there. So let's get into the idea of the Docker file. So it's a defined set of instructions designed to create an image. These are not shell scripts, but they look an awful lot like shell script. The process as you start on one line will not be running on the next line. So if you want an entire command to run with a Docker file, you use the and symbol. So an example of a command that you would have to chain together is, say I want to do an apt-get update and I want to run an apt-get install, git and the program Python 3. So you have to chain the command together with an and symbol. Because if you did it with apt-get update on one line and apt-get install on the next, it wouldn't function correctly. So an example Docker file is here, from all capital Debian stretch slim. We have a maintainer of a company here, CTSIT, and then run the apt-get update and run apt-get install, and then use curl and install curl and PV. So then run echo Wingardium Leviosa, and then another Harry Potter reference, and then command curl this shuttle visualization from the textfiles.com. So that's a Docker file example. So there's another idea in Docker file of Docker file statements. So there's this from is always the first line in a Docker file, and then you have a maintainer. It can usually be whatever, some company at some address. And then there's run command. So the run command waits for it to finish and saves the result. And then you might have an add command where you're adding local files from a directory to the container. So you might add a file, a zip file to the container to process when it boots up, or add a JPEG images to the home drive. You will also have this idea of env or environmental variables. So you might specify an environment of a host database into some server address. And then there's this idea of expose, where you want to, what ports are used on this Docker. And then you'll have this idea we talked about earlier with the volumes. So it sets up a persistent or ephemeral volume. So avoid defining shared folders in Docker files, as it will make it host specific. So if there is a shared folder on one specific server that's not on another, specifying that in the Docker file makes it really host specific. So you want to avoid that, because it stops the process or kind of negates the efficiency of Docker. The idea of Docker is that it's not dependent on anything. It runs in any environment. So you don't want to hard code a shared folder that's dependent on one host. There's other concepts like working directory, the user to use. And so an example of this is a Docker build tagged image called redcap 8.2.1, and then that space dot does mean something. So what I'm doing is I have a folder call, I have a folder that I'm in, and I'm running the command docker build redcap 8.2.1, and I'm building it off of a Docker file that's inside this container. So that's generating a container that's based off of a Docker file, that command. So let's get into an idea of container management. So, pardon me. There's this idea of container management where you're doing local management. So this is things like images and containers, they can get out of hand. You can use switches like --rm to automatically remove containers that you need to run once and then remove itself. There's also this idea of the nuclear option. Say that you're on your, I would not recommend running this, the command on a server Docker instance unless like a production server. But say on your local system where you're running Docker, you have 50 Docker containers up and running, and you don't know what's doing what. And so you can run Docker system prune all and plus the volume. So it deletes everything, images, containers, and volume. So I would never recommend that command on a production system or even a staging server instance, but on your local laptop, if you know that you're done, all your development in your Docker instance, that you've done your testing, and you have, a lot of containers running, you don't know what's going on, and data everywhere, you can run that command. It's very powerful. It does a lot, so be careful with it. Just be sure that you know your Docker states before you do it. So Docker Compose. So beyond Docker files run individual, create individual containers, or in single instances of one Docker file, or single instances of one Docker run. So with the Docker Compose file, it can run single or multiple machines and coordinate their functionality. So it's managed by the use of a YAML file, a YAML file, to configure applications and services. It works for production environments as well as testing and development. And it can manage all containers, volumes, and networks that you need to run a system. So an example is that we presuppose that we've built our YAML file, which is a series of Docker files, and they're all connected together. And so you're ready to build the whole setup. You do Docker Compose up, and it reads the YAML file and builds all the Dockers. There is this other larger concept of orchestration systems, and this gets into trying to manage, thousands, hundreds of thousands of Dockers. And so it can do, there's intelligence built into these orchestration systems where they can do automated container management. A couple examples of these are Docker Enterprise Edition and Kubernetes. When I think about automated container management, I always go back to my web example. Say that CNN has an exclusive story on a massive fire in some historic building. They would see the traffic. The orchestration system would see the traffic hitting the servers, and they would spin up more Dockers to handle the load, to handle the requests. So let's think about common commands in Docker. So these are good to know commands on what they do. So there's Docker pull, that's downloading an image from a registry. There's Docker images, that lists all the images on a Docker host. Could be your local laptop, could be a server. Docker build builds an actual Docker image from a Docker file. Docker run runs an image. Docker commit creates an image from a container. Docker PS lists all the running and stopped instances of all your containers. Docker stop will stop a container from running. Docker remove will remove a container. Docker RMI will remove an image. Docker execute will execute a command that in a container. Docker run -ti Debian bash connects to the shell of a container that's running Debian. Docker -machine IP dev2 will show the IP address for the container called dev2, if you created one called dev2. Docker build -t image tag. So basically, like I said, each image or container has this unique ID. If you want it to be human readable, you use the -t to tag an image with a name. And so you use -- and the same concept, you use -- name to name a container with a common name. So software development and project lifecycle concepts. So this is kind of specific to a company called CTSIT, but in this instance, all of us are in some form involved in the software development lifecycle. Docker is one tool. Linux command lines, Gitflow and Vagrant are also tools, but among many that help us develop, test, and release software and services for our customers. So our work feeds into the larger project lifecycle that we support. So taking this graphic into mind, it's an iterative spiral kind of process where step one, you start discovering the business rules of the customer. Step two, you will create a functional specification and a technical specification where you're talking about things about how would you design it, how would it look, and then only on paper, and then how would you implement it. These are all planning stages, and then you might create a non-functional prototype, and then move into a bare bones functional, like an alpha version. Then you'll build tests for the software, and then you'll have the user themselves test the initial version of the software. Then you'll release an alpha, beta, and then maybe a final version, and then you release the software to the customer. But then there's new use cases, there's new features, there's new data to consume in this process. And so then if you follow the arrow out, we're doing a 0.9.0, which might be a beta, a later beta release, and then you go through that cycle, and then you come back out to version 1, and then version 1.1. So it's just a life cycle. It's iterative in nature. And so yeah, that concludes this talk on Docker introduction. So I know there's a lot covered, and the assignments will help with this.